Assalamualaikum. Today we will be presenting lab report 5, which is frictional force. The objective of this experiment is to determine the coefficient of static force of different surfaces. The apparatus include wooden block, rubber covered at one side, 50-gram masses, 10 Newton spring scale, a string, and tabletop. For the theory, force and velocity are vector quantities that have both magnitude and direction. Velocity is the speed in a specified direction which a given object is traveling. Gravity is an attractive force that exists between two masses. The gravitational force that acts on an object on Earth is approximate as Fg equal to mg, where m is the mass of the object and g is the gravitational acceleration. Static friction is the force that must be overcome in order to move a static object. The maximum value of static frictional force is given by Fs max equal to mu s n, where mu s is the coefficient of static friction and n is the normal force. Kinetic friction is the friction that acts on a moving object, and the kinetic forces is given by Fk equal to mu k n, where mu k is the coefficient of kinetic friction and n is the normal force. In this experiment, the frictional force between wooden block and the surface of rubber on a horizontal plane will be measured, and from the plotted data, the coefficient of static friction will be obtained. For the procedure, the mass of wooden block was measured and recorded as m. The apparatus was set up as shown in figure 5.2. The tabletop was stable and horizontal to the ground. The spring scale and wooden block was attached with a string placed horizontally on the tabletop. The rubber side of the block was faced downward. M equal to 50-gram mass was placed on the wooden block. The spring was pulled slowly. Once the block started to move, the spring scale reading was recorded. The value recorded as Fs and tabulated in table 1.1. Step 4 until 5 was repeated for 3 trials. Another 50-gram mass was added on the wooden block, and step 5 to 6 was repeated. The step was repeated until the total of m equal to 500-gram mass was on the wooden block. Step 1 until 8 was repeated. This time, the rubber side was faced upward. The data was tabulated in table 1.2.
In this part, we're going to see the result data of table 1.1, which is rubber surface towards the floor. In the first column, we have masses from 50 to 500 gram with uncertainties of 0.01 gram. In the next column, it shows the total mass, where mass of wooden block with rubber surface, which is 82.29 gram, added with the masses. Since we want to calculate total weight by multiplying mass with gravitational acceleration, the mass in gram needed to be converted to its SI unit, which is kilogram. For example, in the first row, for 50-gram mass with total mass of 132.29 gram, we convert it to kilogram, which result in 0.13229 kilogram. Then we multiply it with gravitational acceleration, 9.81 meter per second. We got 1.30 as we round up for 2 decimal places. For the next column, we have data of static friction force with uncertainties of 0.2 newtons that we obtained from spring scale reading. We took the average reading from 3 readings taken. From the data here, we can see the trend as the total weight increased, the static friction force increased as well. Next, for result data of table 1.2, which is non-rubber surface towards the floor. For the first 3 column, we have the same data with previous slide. We have masses from 50 to 500 gram with uncertainties of 0.01 gram. The total mass, we added the mass of wooden block with rubber surface, which is 82.29 gram, added with the masses. Then we convert it to kilogram and multiplied with gravitational acceleration 9.81 meter per second for the total weight in Newton. From the data, we can conclude the static friction force increased as well as the weight increase. It's just that compared to the previous slide, the friction force produced between the floor and the non-rubber surface not as high as with the rubber surface. We move to the next part, which is data analysis. First question, draw and label the free diagram of wooden block. For rubber surface, there are 4 forces constructed from x and y axis. At x-axis, the diagram shows frictional force to the right, opposite direction to the applied forces. For y-axis, the normal force to upward direction while weight is downward. For non-rubber surface, it produces 3 forces, which are normal force to upward direction, weight to downward direction, at y-axis, while applied force to the left of x-axis with no frictional force, as a frictionless surface. Second question, plot graph of static friction force against normal force. Both for rubber and non-rubber surface exert direct proportional between static frictional force versus normal force. Next, we move to third question. Calculate the coefficient of static friction using the gradient obtained from the graph. Since the gradient represents the coefficient of static frictional force, we calculate the gradient by using formula m equal to y2 minus y1 over x2 minus x1. We got 0.76 for rubber surface, while 0.45 for non-rubber surface. Next, question number 4. Compare and discuss the coefficient of static friction obtained. The coefficient of static friction for rubber surface is greater than non-rubber surface towards the floor. This is because the rubber exhibits more resistance at initial motion due to its elasticity and surface grip compared to non-rubber surface.
I'm going to discuss some key concepts related to friction and how they apply to everyday situation like stopping a car. Let's start with a crucial safety feature, anti-lock brake. The question is, how can anti-lock brakes stop a car in a shorter distance than regular brakes? The answer lies in how they manage friction. Anti-lock brakes prevent the wheel from locking up. Why is this important? Because it keeps static friction working, and static friction is always stronger than sliding friction. When you reach lock, you transition to sliding friction, which is less effective at the stopping car. Now, let's look at an experiment we conducted to understand the coefficient of static friction. The question asked, from your experiment, which material has the highest coefficient of static friction? Does this agree with your hypothesis? And what do you think determines the coefficient of static friction? Our findings show that the rubber surface had the highest coefficient of static friction compared to the non-rubber surface. With a total weight of 5.7 newtons, the rubber surface produced an average static friction force of 4.9 newtons, resulting in a coefficient of static friction is approximately 0.86. In contrast, the non-rubber surface only produced 2.4 newtons, leading to a mu of about 0.42. This definitely aligns with what we would expect. Rubber, being a more textured and grippy material, provides greater resistance to motion. This leads us to the conclusion that the coefficient of static friction is primarily determined by the nature and texture of the material. Finally, let's consider what happens once a mass begins to slide. Does it move smoothly, or does it undergo stop and go motion? And why? Our observations show that it moves in stop and go motion. This happens because it takes more force to initially start moving the mass due to static friction. Once it starts to move, the friction becomes kinetic friction, which is less than static friction. This reduction in friction allows it to slide, then it might momentarily catch again and then slide again, creating that characteristic stop and go movement.
Number 2, there are two materials used to determine the frictional force. One of them is the rubber and the second one is the wood. By comparing the two materials, the rubber has a greater frictional force. This is because its material is soft and flexible, making it deform easily, creating more surface touching. Another thing is it increases microscopic interaction. Basically, for example, tiny bumps scrape each other, thus increase friction, while the wooden is hard and not deformed much, less contact with the surface, and its materials is too smooth and slide more easily. Number 3, we are talking about the relationship between static frictional force versus normal force. The following formula, F equals mu n, representing coefficient is the gradient m. And the graph shows that it is linear because the formula F equals mu n is the same as y equals ms plus c. This also shows that the coefficient static friction rubber side is greater than the wooden side, and high internal exhibited by rubber over white region. Number 4, this experiment can help understand how friction affects motion in real life situation. For example, the anti-lock brakes. How it works is it prevents wheels from locking up and skidding. And the wheel will have kinetic friction between tire and road with more resistance in motion. In conclusion, the highest coefficient of static friction is the rubber material rather than the wooden blocks. Others agree with the hypothesis the rubber will produce a greater amount of frictional force compared to the wooden sides based on the data. The coefficient of static friction depends on the two materials in contact. The type of surface also plays a role. A smoother surface will result in a lower mu, while a rough surface will increase mu. Number 6, while the experiment is complete, there are some minor errors that occur. For example, parallax error where the eye is not aligned with the measurement scale on the spring scale. Number 2, additionally, inconsistency in pulling angle, uneven surface texture, or difficulty in identifying the exact moment the block started to move. Overall, the results supported the hypothesis and demonstrated a consistent trend, making the conclusion reliable.
And for the conclusion, the coefficient of static friction of different surfaces can be determined, which is the coefficient of friction for rubber surface is 0.76. Meanwhile, the coefficient of friction for non-rubber is 0.45.
Finally, here is all the source that we consulted for our lab report. That is the end of our presentation. Thank you for tuning in.